God, this is so difficult. No. Okay, so this, it should... Okay, it's not going to work. It should... Okay, that's better. Okay, so can everyone see alright now? There's a slight lag. Why is it doing that at the bottom of the screen? Okay, there's a very slight lag. I just need to work out how long it's lagging because it won't make sense when I'm talking. Okay, we're getting there. Right. Right. So that thing's annoying at the bottom. Okay, I need to work. Okay. Right. So there's a very slight lag, so just let me know. Sorry about this, it's really difficult. Okay, but we're on. Okay, so we're going to cover two things, and then you can ask. We're firstly going to look at deriving the properties of an AR1. So this was about halfway through lecture 2. And then we'll go on to go over again the definition of the lag operator and looking at stationarity of ARP models. So we only touched on this a little bit in the lecture. So again, there's a video clip on my channel which goes through this. So hopefully you've watched this, but I'm going to go through that material again using the lecture slides. Okay, so I've made some new lecture slides which should make the derivation of the AR easier to understand. Okay, so we're going to look at deriving the mean, the variance, the covariance, and the autocorrelation function of an AR1 process. Okay, how do we... Alright. It's lagging. Okay, so we want to derive the mean, the variance, and the correlation function of an AR1. So there's a few ways to do this, but the simplest way is to put the AR1 into its lag operator form. Into its MA infinity form. So what I mean by that is what we covered in lecture was, we can see the recursive structure here to an AR1 process. YT depends upon YT minus 1. We could keep recursing back forever and ever and ever. We can keep plugging in back and back, and we can write YT as an infinite, we can write YT as a function of all the past shocks epsilon t. So we first take the definition, then we come back substitute once. So definition R1. Okay, then this holds every time period. So it also holds one period back. So all we do is recur back one period. So it's lagging a little bit here. So the definition of if the AR1 holds any time periods, all we've done is lag back once, and then we're going to plug it in here and expand it out. So we've recursed it back one period. So recursing just means we've gone back one period. So we're going to plug it in to YT minus 1. This will give us then the first recursion. Okay, so we can do that now. We can put this in, and we can expand out. So all we've done is substituted in and gone back one. When we plug it in and we expand out, we get down to here. Okay, so it'll be useful as you're going through. As I said with these problems, it's easier to do if you sit and work it through on paper. So all we've done is plugged in YT minus 1 and expanded out. There is a constant term, the mu. I don't see what you mean. This is the constant here. Oh, sorry, that's a typo then. Sorry, let me go back. Yeah, so you're right. Sorry, that's a typo. That should be mu there. Yeah, that should be mu. Sorry about that. That should be a mu. Okay, so this holds every time period. Sorry, it's lagging. It's really annoying. Okay, so there should have been a mu there. Sorry, I will edit these. I'm going to send out these extra slides for you to print when you watch this again. So I'll put the mu in there. Okay, but the idea is it holds every time period. So we can work out yt minus 1 and plug it in and expand it out. Okay, so if you do this, then we get down to the next slide. Okay, then we can do it again. We can now work out, well, what's yt minus 2? And keep going back. Okay. Well, there's another way of writing this. We can see, when we go back one period, we have mu plus mu phi 1, which we can write in its sum form here. And again, we can write this part here in its summation form. So this will be, you'll see why it's reduced as we move through, because you'll see a pattern that emerges. So this is recursing back one period. So this is the first recursion, R1. We've gone back just once. Okay, so all I've done in the red part underneath is just to write both of these expressions in a summation form. So for example here, we have, when we expand this out, we'll get mu plus mu phi 1. When we expand this out, we'll get the above here. So you'll start to see a pattern that emerges. Okay, so this is recursing back once. We can now plug in yt minus 2. So we can recurse back again. So again, we can work out what is yt minus 2, and we can go back again. And we'll see the same pattern start to emerge. So we'll go back. So again, all we're doing now is going to plug in yt minus 2 into here. Sorry, it's lagging, it's so annoying. Okay, so again, as I said, so we're going to now work out yt minus 2, and again, there should be a constant here, there should be mu. Plug this into yt minus 2, and then we get down to here. So this is from the second recursion, going back twice. So all we've done is back substituted twice, and again, we get this expanding here. And again, all the red term does is to write this in its general summation form. So we can see here, we can rewrite this in its sum form, we can rewrite this. This is just a more succinct way of writing it. So we can see, when we've recursed back twice, we've got the exact same looking sums as before, we've now summed up to 2 here. Whereas before we've summed up to 1. Okay, so we start to see a pattern emerging. And again, you can see here, yt minus 3. At the second recursion, it's gone down to yt minus 3, phi 1 to the power 3. So this here is just phi 1, 2 plus 1, yt minus 2 plus 1. So this is what's happened at recursion 2. So we can start to see the pattern that's emerging here. What we can see is that when we've substituted back twice, we get this sum forming up to 2, this sum forming up to 2, then we get phi 1 to the power of the recursion plus 1 minus yt minus the recursion plus 1. Okay, which is exactly the same, and we could keep going. So if you did it again and again, you keep seeing this pattern over and over again. This is what I was saying in lectures, is we can now do this for an arbitrary number of recursions. We've done it for 1, we've done it for 2, we can now just do it for an arbitrary number of times, call it j. So we can go back now. So just to recap what I said there, so this is from the first recursion. This was from R1. And this was from R2. Recursing back once, recursing back twice. Okay, so I've written it in these form, and again I'm going to give out these notes, extra notes. We can see, when we go back once, there's the same pattern that emerges. Here, we get the sum, we can see they look very similar. When we go back once, we sum this term up to 1. then when we've gone back twice, we summed it to 2, and the same for this sum here. Here, it's summed once, and then afterwards, and beneath, we see the sum twice. Okay, and what we can also see a pattern emerging on these powers. So this was from the first recursion, and this was from the second recursion. We just get this power is the recursion we're at plus 1, and this is the recursion we're at plus 1. So hopefully you can see the pattern that's emerged here. We've done it once, and we've done it twice. And we can keep going. So we could do it a third time, and a fourth time, and the same pattern will keep going. So you could use that to motivate the final derivation, but then you go down. So the next slide then just does it, goes dot dot dot. It's just for an arbitrary number, j recursions. Goes dot dot dot. It's just for an arbitrary number, j recursions. Okay. So again, just like before, at recursion 2, we summed to 2. Now we just sum to j. We've done it j times. This is recursion 1, recursion 2, and this is recursion j. When we've recursed j times. And again, here at recursion 1, we summed it to 1, to 2, and now we do it to j. Here, this is recursion plus 1, recursion plus 1. So here, it's just j plus 1, j being the number of recursion. And again, we've got minus 2, which is 1 plus 1, minus 3, which is 2 plus 1, and then minus here, which is just minus j plus 1. So hopefully you can see the pattern that's emerged. Okay, so then at this line here, so is everyone following then? Right, say otherwise. If not, does everyone follow why the AR1 can be re-expressed like this here by going back j periods, by recursing back j times? Okay, so as I said, it's clearer to just work through this by hand on your own. So it's often useful before lectures if you sit and actually look at these before you come, because it's very difficult in lectures to go through these derivations step by step in that time we have. So everyone's following, yeah? So again, as I said, I'm going to give out these lecture notes, these extra slides. And just to check, is my voice coming at the same time as the derivation? Just say yes. Because on my screen it looks lagging, but is the voice coming as I write? Okay. Right, so on this slide then, we've just gone back once, twice, and an arbitrary number of j times. Well, we can keep going back forever. So the next bit then is to let j go off to infinity. So again, we can go back as many times as we want. So the next slide is then we go back forever. Okay, well, do it line by line. Again, we're assuming stationarity. We're going to assume that this AR1 coefficient is less than 1 in absolute value. Okay? So that the limits exist, otherwise they'll blow up. So we can first look at what happens to the first part. Well, the line above is just the recursion up to j. We're now letting j go up to infinity. So all we do is take the limit of this as j goes to infinity. Well, this is just a geometric progression. This is just, remember, sigma s equals naught to infinity, letting j go to infinity, of phi 1 to the power s. Well, to write it out, it's 1 plus phi 1 plus phi 1 squared plus dot dot dot, which is just an infinite geometric progression in phi 1. And again, if phi 1 is less than 1, as we assume, then the limit is 1 over 1 minus phi 1, which is why we get this here to the left. Letting j go to infinity, well, this just becomes this here. Okay, and what this is just by definition is a geometric progression. So you'll see this geometric progression a lot. You'll see it come up again and again. So you have to be comfortable using this. So again, if anyone's not following, just say on the stream. Okay, so then we get the first part then. We've derived the limit of the first part of the expression using the geometric progression formula. Okay, so then we can now look at what happens to the middle term. Well, we're assuming that phi1 is less than 1 in absolute value. Yeah, so if the phi, yeah, so going back there, we can see we have to have phi1 less than 1, otherwise it'd be infinite. If phi, let's take the case that if phi equaled 1, going back, we can see this limit wouldn't exist. If phi equaled 1, we get 1 plus 1 plus 1 plus 1 an infinite number of times. Therefore it would blow up. So this limit wouldn't even exist if phi was 1 or greater than 1. So we had to have phi was less than 1, such that the limit existed. So this is what I was talking about in lectures. The only thing left when working with limits is to just have the assumption required such that it doesn't blow up to infinity. So here we can see phi1 less than 1, that it will exist. So is everyone clear on that? We can see what happens here. If we plug in phi1, 1 or greater than 1, this is going to blow up as j gets bigger. Okay? And the same thing for the second term then. Again, assuming that phi1 is less than 1 in absolute value, then we know then that this term will tend to naught exponentially quickly. Take the case, for example, of, say, 0.5 to the power j. As j goes off to infinity, this tends towards naught extremely quickly. If you draw it in a graph, it's going to go down to naught extremely fast. Okay, so this term will tend towards naught exponentially quickly, which means that this whole thing will tend towards naught exponentially quickly. So that's why we get this result. So again, phi1 less than 1, we get this, that this second term tends towards naught, it drops out. Another way of seeing this is just essentially saying the effect of the faraway past is dying away as we go back and back. Is that okay? It's back. Okay, so sorry, I'm still getting to grips with this. Hello, back. How about now? Back. Hello. It should be okay. Is everyone else? Can anyone else here? Is it back? Hello. Hello. Okay. So is everyone clear why the second term drops out? Why this term dies off and goes out? Okay. And then finally then, so it simplifies. So again, this drops out. So finally then, well, what happens to this term as j goes to infinity? Well, just replace the j with infinity here. So again, this becomes this. And again, the limit will exist because this phi1 is less than 1. So again, we've also used the fact that this phi1 is less than 1 in absolute value. So it's at the limit of this exists. So that's it. We've got the first part, which comes to this here. The second part is not. Then we get this last part here, which is what we had in class. Okay? So all we've done is seen what happens to this. This is just the sum to j. So of course, if we go back to infinity, we get the sum to infinity. And that's all that we've done here. So then we have derived the MA infinity process of a... Which one? This one? The second term or the third term? 2 or 3? Which one? Do you mean this one? Number 2? Which part do you mean? Hello? So you need to respond. I don't know which one. I don't know which part you mean. Why does this part die out? The second part. Hi. Okay. So because when phi 1's less than 1 in absolute value, then this term tends towards naught as j goes to infinity. Yeah? If phi 1's less than 1, this term goes towards naught as j gets bigger. So we've got something between, let's say, so take for example the case where phi 1 equals a half. Yeah? Then, well, 0.5 to the j plus 1 to the power of this tends towards naught as j goes to infinity. Because we're going to get half times a half times a half and so on. It's going to converge to naught. So we have that this term converges to naught exponentially quickly. Yeah, is everyone clear why that goes to naught? Because we're taking it to a power j. So a half times a half times a half. Remember the power multiplies it together, j plus 1 times. Yeah? So again, just draw this on a graph, think about it. So anything between 1 and minus 1, anything less than 1 and greater than minus 1, to a power, as that power gets bigger, tend towards naught exponentially fast. And that holds for any phi 1. So again, 0.9 to the j plus 1 tends toward naught as j goes to infinity, and so on. Yeah? So because this term tends towards naught exponentially fast, then when we multiply that, so this will also go to naught as well. Because remember, y just lies, it's just some finite value. So y, say interest rates or so on, is just some number. So we multiply y by something converging to naught exponentially fast. Then of course the two multiplied together also converge to naught exponentially fast. Okay, so is everyone on board why term 2 drops out? This term drops out. So this phi, remember, this phi 1 is how the past, how much y into the past affects now. So it's saying that it's going to be a much smaller effect. Okay, so the second term drops out. We can then now look what happened to this term as j goes to infinity. Well, it's very straightforward. As I said here, all we have here is this is the sum to j. So now we'll just let j go back to infinity, so it just becomes this. Assuming the limit exists, which it will do because this phi 1 is less than 1 in absolute value. So again, the limit exists because these phi 1 powers go to naught very quickly. So we've shown what happens to the limit of each part. So we've broken it up. So to recap, we recurse back once, we recurse back again, we saw a pattern emerge, we then recurse back an arbitrary number of times, called it j, then we let j go off to infinity, and we found the condition we needed for that limit to exist, which was phi 1 less than 1. Okay, so any of these types of questions for the armor 1, and so on, it's always the exact same method. So this is why, as I said, it's useful to sit and work through it on paper and go back. It's not always obvious to see in a lecture immediately what's going on. But once you understand this you'll see this again and again. Okay, so again, as I said with this course, once you do the classes and read the notes and etc., eventually everything will start to click into place. So, we have done the final result. We've derived the MA infinity representation of an AR1. When it's stationary. So we've derived the MA infinity for a stationary AR1. Okay, so this is just then an example of the Wold Theorem. The Wold Theorem says any process which is stationary can be written in an MA infinity form. Well, this has the MA infinity form. Remember in lecture we called this alpha, and these coefficients would be theta s. This would be a general MA infinity. So this is just a particular MA infinity, which is useful then because we've got the general formulas for the mean, the variance, and the covariance of an MA infinity. So this is why we're doing this. We're writing it in this form because once we have the MA infinity form, remember that yt is equal to this. All these are equivalent. Yt equals it. So the two things are the same. They're exactly the same thing. It's just re-expressed a different way. Okay, so that's crucial to realise here. The two things are the same thing. We've re-expressed the AR1 in this form here. They're both exactly the same. So therefore, obviously, they have all the same properties. So if we want to look at what's the mean, the variance, and the covariance of an AR1, well, we can just work out what's the mean and the variance and the covariance of this particular MA infinity here. Okay, so any questions so far on how we got to this MA infinity and why we're going to use it and how we're going to use it? Because then, once everyone's clear on how we got to the MA infinity, we can then, so again, this just recaps. So again, crucially, under this condition, we have the AR1 can be re-expressed in this form here, the MA infinity representation. Okay? So then now we're done. So we can go back to the general formulas that we had, which we derived in lecture. So remember in lectures, well, in the video clip, we derived the mean, the variance, and the covariance for an MAQ. Then it let Q go off to infinity. And we had the properties of an MA infinity. So again, to recap, the start of lecture 2. So this is general. This is for a general MA infinity. What I mean by that is these coefficients could be anything, alpha and theta s. Just says an MA infinity is any process which can be written in this form. Well, what we can show is that the mean is alpha, the variance is this, and the covariance function looks like this. So again, watch the video clip on deriving the properties of an MAQ. And then we did it for an MA1 in the lecture. We're going to do it for an MA2 tomorrow in the class, and the video clip goes through the general case. And then once we have the properties of an MAQ, we let Q go off to infinity, as we talked about in the start of lecture 2. So again, all these, we can, in terms of this question, we can take all these as given. So we're going to use all these results now to derive the mean and the variance and the covariance of an AR1. So in our case, well, for an AR1, we have a MA infinity form where alpha is mu over 1 minus psi1, and the theta s is psi1 to the s. So now all we're going to do is just plug these into all these formulas and work out what's the mean, the variance, and the covariance. So from now on in, it's just algebra. So again, of course, there's a lot going on here, but once you understand the intuition and what we've done, from now on in, you're just plugging in and rearranging. Okay, so it's good to separate what's the intuition, what's the concept, and what's just algebra. So here, once you understand what we've done here, we're now just plugging in these coefficients into these formulas on the left. Okay, any questions on this? So just go on the chat if you have a question. Okay, so just reiterate, this is a general MA infinity. In our case, we have it evaluated at these coefficients here. So again, well, alpha is just this. So we know the mean then must be this. So we derive the mean. We know the mean of an MA infinity with coefficient mu over 1 minus psi1 is just this. So we've got the mean. We can then derive the variance. So again, general formula here. We're now going to plug in our particular coefficients. So we're going to plug them in to here and expand it out. So, well, we can do this. So we just plug in theta 1s. And we get this. So again, we just plugged in theta s equals psi1 to the power s to here. Then we're going to square it. So then we will get well, this is just a geometric progression in phi1 squared. So if we expand this sum out, we're going to get phi1 to the 0, which is 1, plus phi1 squared, plus phi1 squared squared, and so on. This is just a geometric progression in phi1 squared, where we know that phi1 is less than 1 in absolute value, so therefore the square of it is also less than 1, because something less than 1 squared is obviously also less than 1. Okay, so again, under the stationarity assumption, we also have that the square of phi1 is also less than 1. So then we have a geometric progression now in a variable which is less than 1. So we know then we can just use the geometric progression formula. Remember the general formula, 1 plus x squared plus x cubed forever is equal to 1 over 1 minus x, when x is less than 1 in absolute value. So if we just evaluate it at x equals phi1 squared. Okay, so that's all we're doing here. So again, as you should hopefully see, you need to be comfortable working with this geometric progression formula. So then we're done then. So we get the result. So this is the variance then of an MA of an AR1. Okay, so hopefully everyone's following then. So then we can now plug in the coefficients to get the autocovariance function. So again, we have the general definition. We're now going to plug in our coefficients into here. So again, theta s equals this. So, and this holds for any s. So theta s plus k, well, that's just phi1 to the s plus k. The powers just have to match here. Okay, so we can plug these both in. And we can simplify down. So we can plug them in, and then we get down to here. And then we've just used the product rule for powers. So remember, when we multiply, the powers add. So they add together. So we can re-express it like this here. Okay, so remember, if we have a to the x times a to the b, a to the y, we just have a to the x plus y. Okay. So then we can simplify down. And again, we can take the k part outside, because the sum only depends upon s. So therefore we can take this part, we can break it up and take the k part outside, because obviously it's not a function of s. And then we can see, well, what's this? Well, this is just the variance from before. This is just the variance as we saw in the previous slide. Remember, before we simplified down and used a geometric progression, this was what the variance looked like. So this here, we get then to the final result. Okay, so we showed this earlier. Remember, gamma naught is just the variance. Gamma naught, well, remember gamma k is the covariance of yt and yt minus k. At k equals naught, this is just the variance. It's the covariance of yt with itself. And if you look at the formula, it's just going to be the variance. So you'll see these two interchange. Gamma naught is just shorthand for the variance of yt. Okay? So that's it. We've shown then the covariance at lag k is equal to phi1 to the k times by the, and this holds for any k. And remember, when a question asks you to derive the covariance function, you're deriving it for every lag. This holds for every k here, so we've written out the whole function. So again, one example of a way to lose marks in the exam, for example, would be to just write it and not state it holds for every k, for example. So when you're asked to find the function, you've got to find it at every lag. You've got to state it at every lag. Okay, so we've got the whole covariance function then. So we can then from this get the correlation function. Again, remember, the correlation function is just the correlation between y and yk pairs back. And for a stationary process, well, by definition, it's just the covariance divided by the variance. So this is just the definition of the autocorrelation function. Well, it's very simple for in our case then. Looking back from before, if we divide gamma k by gamma naught, well, gamma k, it's going to come out here. So again, remember, gamma k, we just showed this. So divide both sides by gamma naught, and this will drop out. Okay, so that's what's happened on the next slide. So the correlation function then just is phi1 to the k. Okay, and we can plot this then. So this tells us, so what's the benefit of this? Well, this tells us how strong the correlation is. Remember that this is the correlation between yt and yt minus k. So as big the so k is the lag. So remember, k is we have the correlation of yt and ytk pairs back. So k equal 1 will mean the correlation between yt and yt back one period. At k equals 2, it's the correlation between yt and yt back 2 period, and so on. What is S? Where's S? Where is, what's S? I don't know what S is. Do you mean T? I can't see S. I don't know what you mean, sorry. The K is just a lag. So K is, remember, it's a stationary process. It doesn't matter where we are in time, because we know that all the moments, the mean, the variance, the covariances, and the correlations are all the same, no matter where we are in time. I don't. You have to write it again. I don't know what you mean by S, but K is just how far we're lagging back into the past. Okay, so is everyone following this then? Is everyone clear on what we derived here? Okay, so this is a very powerful result then. It tells us that the correlation but there isn't an S. I'm struggling to see what you mean here. Do you mean T? Oh, I know what you mean. Okay, okay, this here, okay, it doesn't matter what we call this. This just, I know what you mean, you mean this, right? This is just a succinct way of writing an infinite sum. It doesn't matter what we call this. This just means when we expand out, we will get 1 plus phi 1 squared plus phi 1 to the 4, and so on. So we can call this, you can call it whatever you want. You can call this whatever you want. So you could call it L. You'd have L here, and you'd have L there. Yeah. So the subscript here doesn't matter. This is just a way of succinctly writing an infinite sum of variables in one term. Is that clear? So it's just an index. It doesn't matter what we call it. So there's no real interpretation to S here. It's just notation. We can call it anything. It just means that what this means is take the sum of this function here, where we evaluate S equals 0, then add on S equal 1, then add on S equal 2, and so on. So you should see that what we call this doesn't actually matter. It's just an index, just a way of categorizing an infinite sum into one term. Is that clear? Yeah? You're going to have to say, so is that clear? So say it again, or... So another way of saying it is for example, if we have the sum let's say the sum of, say, I don't know, x to the a from a equals, say, 0 to infinity is just exactly the same as the sum of b equal 0 to infinity of x to the b. Yeah, the two things are exactly the same, it's just another way of writing it. So that this is just an index, doesn't matter what we call them, it's just a way of, yeah. Okay, so again, I see what you mean, it can be confusing because you've got lots of subscripts going on. But yeah, this S was just notation picked completely at random. Okay, so the only crucial notation here is the K, which is the lag, which represents the lag between now and K periods back. And of course T, which is time, which in our case doesn't really matter because, let's go back. Again, it's also, because we're assuming stationarity, the correlation just depends on the gap, not where we are. So the correlation, remember the correlation or the covariance between, say, y1 and y2 is the same as the correlation between, say, y100 and, sorry, one sec, between y100 and y99 and so on. So it's just the gap that matters. Okay, so this is from the stationarity assumption. Okay, so this is a powerful result then. This tells us the correlation of an AR1 process with itself k periods back is this phi1 to the power k. So we can see it makes intuitive sense then. If phi1's positive, well, remember what phi1 is doing here. So again, it makes intuitive sense. Phi1 is how yt last period affects now. So this, and again, if we go back again, when we keep recursing back, we can see, well, if we go back, if phi1's positive, then it means yt depends positively on yt minus 1. And if we go back again, well, yt depends upon yt minus 2 by phi1 squared. Remember when we did the expansion out, and we kept going back in the recursion, we could see the way that yt is impacted by 1, 2, 3 periods back is just this phi1 to this power. So that's the intuition as to why we get this. If we keep looking back at your recursions from earlier, how yt minus 2 impacts yt by phi1 squared. Yt minus 3 impacts yt by phi1 cubed. So yeah, recurse 1, recurse twice. Yeah. So go back and you should be able to see how, you can see intuitively why we get this result, why it comes out like this. Okay, it makes intuitive sense. If phi1's positive, then yt is correlated positively with any time in the past where this correlation dies away really quickly. Okay, so again, we can draw this in a graph. Take the case where phi1 equals a half. So all this is done is just plot the correlation function against the lag. Okay. So again, so here we just plot 0.5. So this is from the lecture notes, 0.5 to the k. So we can see, well, the correlation, lag naught, we always get 1. Okay, the correlation with itself is always 1. So at lag 1, we have a half. At lag 2, we have a half squared, a half cubed, and it goes down. So we can see this goes to 0 as k goes to infinity, this particular pattern. So this just says the correlation of yt with itself in the past is decaying exponentially quickly. And of course, the bigger is phi1, the slower this will dissipate. So we can see again a similar pattern. It still reduces, but at a slower rate. So this will allow stronger correlation with the past, which also makes intuitive sense. Because if phi1 is bigger, it means yt depends more strongly on the past observation. Okay. If phi1's negative, then we're going to get an oscillating pattern. Yt depends negatively on yt minus 1, but that means yt minus 1 also depends negatively on yt minus 2. So we get negative, negative. That means that yt is positively correlated with yt. So this just plots minus 0.5 to the k, and hopefully see intuitively why we get this oscillating pattern. And again, it dampens out very quick. We get the exact same similar thing for phi1 equals minus 0.9. We get this oscillating pattern, but again, it just dies down a bit slower, but eventually it does die down to naught. Okay, so we've seen a visual depiction then. This is the reason why the correlation, deriving the correlation function is really important. It tells us what kind of correlation patterns are consistent with a particular model. So we've seen the particular types of correlations which are correlation patterns which are possible with an AR1. Okay, so this will be useful when it comes to practice then, because when we look at the sample correlations, which we're going to talk about in lecture 3, let's say the sample correlations look a little bit like this, then it might suggest that the true process was an AR1 or something like an AR1. So this is why we do this, to give us a feel for what kind of correlation patterns different processes will allow. Okay, so that's it then on deriving the properties of an AR1. So are there any questions on this? And remember then, so for the exercise class, there's a question on the ARMA 1-1. So it goes around deriving the properties of an ARMA 1-1 in a slightly different way. But again, you can do this for the ARMA 1-1. You can do the exact same thing we just did here for the ARMA 1-1 model. Keep recursing back forever and ever, work out the pattern, get its MA infinity form, and then plug all of the coefficients into these general formulas. Okay, so once you understand it for the AR1, you understand it for anything else. Okay, and as I said, anything in terms of exam type material will have to be something which is doable, obviously in a short period of time, and not too much algebra. Okay, so that's everything then on the AR1. So let's now, I don't know how did that get there? Okay. And again, this from the lecture slides, well, this is just the correlation patterns from an AR2. So an AR2 is yt equals mu plus and again, we don't cover how to derive these. We don't cover it will be too advanced to derive these, but again, it just gives you a visual plot. Where's it going? This just shows you that, of course, more complex models will allow more complex forms of dynamics. Okay, so we can see, this just gives you some examples. So we can see that this is more complex relative to an AR1. For an AR1, it doesn't allow this here. But we can see eventually it starts like an AR1, and so on. Okay? So this just gives you the notion that as we make the model more complex, it allows more complex forms of correlations, of dynamics. Okay? Which is obviously going to be useful if our data has complex forms of correlation pattern. Then it would suggest that we need a more complex model, which is what we're going to start talking about in the next lecture on Friday. Okay, so this looks at the lag. We're now going to the second half. We'll look at the lag operator and stationarity of ARM models, especially ARP model. So again, I went through this quite quickly in the lecture, but I did make a video clip on this, which says everything I'm going to say. So again, it's always useful to read the notes and watch the video clips before the lecture, because there's only a short amount of time to cover this material in lecture. Okay, so the lag operator, defined as L, is just something which satisfies this here. So again, the operator isn't a function, it's not a polynomial. An operator literally performs an operation on something else. So LYT just lags back the variable one period. That's what the L does. We could lag back twice. Apply the operation twice. Well, this is just L of YT, which is just YT minus 1 from above, which is just YT minus 2. As we'd expect, we've lagged it back twice. Okay, we often write this shorthand as L squared YT. But just to be clear, there's no notion of L squared. We can't square this operator. It's not like a number like 2, where 2 squared is 4. But this is just shorthand notation. So L squared means go back twice. L to the power k would then be lag back k periods. Yeah, just means apply the lag k times. Okay. So this lag operator is really useful because it allows us to write complex processes in terms of what's called its lag operator form, which will become clear. But let's look at one key property of, which I spoke about in the lecture. There's one key property of the lag operator, in that it behaves like a polynomial. What I mean by this, let's suppose that, and this should just be yt here. Let's say we want to perform this operation on yt. Well, we can work through and go through. Okay, well, this first part here, this is just the 1 plus L of yt. Yeah? And then go down. Well, by definition, this is yt minus 1. Then we can then apply the 1 minus L to this, which will give us this minus L of it. So we go down to here. Okay, so all we're doing is applying this operation, a set of operations to yt. And then if we lag this back one period, well, we're going to get yt minus 1 and yt minus 2. And then work down, we're going to get the yt minus 1 cancel out, and we'll get this here. Okay, so we covered this in lectures. All we've done is just gone through and worked out what this operation on yt will give us. So this particular operation will give us yt minus 2. So when I say that L behaves like a polynomial, what it means is we could just have treated L as if we could expand it out like a quadratic, and it will be equal to this here. So if we perform 1 minus L squared, remember 1 plus L, 1 minus L, if it was a polynomial, would equal 1 minus L squared. So what this means is, instead of going out longhand and working out all these operations separate, we can just expand out this set of operations as if it were a polynomial in L, and then apply that instead. So if we did that here, well, we get this, and the lag squared of yt is yt minus 2. So the two things are equal. So is everyone clear what I mean by when I say that the L behaves like a polynomial? What it means is if we got many operations all applied one after the other on y, we can expand them all out as if it was a polynomial, like we did here, and then just apply the operation we get at the end. So it's much simpler. Okay. So this is it's key that you understand this, because we're now going to use this idea to then write AR models in what's known as a lag operator form, and it allows us to we're going to study the properties of them using this result, that if we have a system of operations all applied one after the other, we can just expand them out as if there's a polynomial and apply that instead. So I think everyone's following then, because no one's said anything. So this is what the next slide gets at then. So take an example, we have an AR2 model here. Right, well, we can just rewrite this as, we can put it in its lag operator form. We're going to get mu plus phi 1. Well, yt can be expressed like this, and yt minus 2 can be expressed as yt squared. L squared of yt, sorry. Okay, so we just use the definition of the L. Well, that's all we've done then. So then all we've done here, we can take all this to the left hand side. We can take all this over here, and we get this up here instead. So this is just algebra now. So we can take all this and we can just rewrite the AR2 in its lag operator form. So is everyone clear how we got to here? Okay, so this is the term. This term is then this here is the AR2 in its lag operator form. Okay, so we can see by doing this we've got rid of the yt minus 1 and yt minus 2. We're now going to use the result that we can treat this. This is just a system of operations on y. We can treat this as if it was a polynomial. Okay, which is what we do here. So we want to now re-express this in an equivalent form. Well, we know that we have that this here is just a quadratic in L, and we know that we know that the properties of the lag operator remain, treating it like a polynomial. So we can, if you want, expand all this out. So all we've done here is, so this is just algebra, and all we've done here is said, so people have asked what is lambda 1 and lambda 2? Well, we want to rewrite 1 minus phi 1L. We want to factor it out. Well, we can, so this just goes back to your school level algebra. So we want to find these roots. So lambda 1 and lambda 2 are to be found. So lambda 1 and lambda 2 are obviously governed by whatever these coefficients are, phi 1 and phi 2. So all we've done here is, this is just a quadratic in L. We normally do a quadratic in X, but it doesn't matter. It's just a quadratic now in the variable L. So we want to find lambda 1 and lambda 2, which make these two sides equal. Well, in terms of the general idea, we don't actually need to find them. Or we can say, whatever phi 1 and phi 2 are, we can always find these roots of the quadratic to factor out like this. So we don't actually even, in terms of the general theory, we don't actually need to state what they are. We can see by basic algebra, we can always find some lambda 1 and lambda 2 to make these two sides equal to each other. Yeah, but if you wanted to find them, it's relatively straightforward. Well, we can expand out the left-hand side. The left-hand side, if we expand it out, we'll get 1 minus lambda 1L minus lambda 2L plus lambda 1 lambda 2L. Okay, so this is just, we can then just match coefficients. We're going to get minus lambda 1 plus lambda 2L. Okay, so we just match. So we have, well, these two are the same. So we now have, obviously, lambda 1 plus lambda 2 equals phi 1. And lambda 1, lambda 2 equals minus phi 1. Sorry, minus this equals. Yeah, because remember, this would be minus this. Okay, so all we're doing is just matching coefficients. Matching this with this. So we can find these roots. These roots will satisfy these two conditions. So that should be lambda 2, sorry. Phi 2, sorry. Yeah? So we're just comparing coefficients here. So we just match this. Because of course the two have to be equal to each other. Okay, so is everyone clear how we can get the lambda 1 and lambda 2? So again, in terms of a question, this is one quick way to find them. The roots added together have to equal the phi 1 coefficient, and multiplying them together has to be negative the second coefficient. Okay, or you could use the quadratic formula. You know, the b minus b squared plus or minus square root. Sorry, what was it? Minus b plus or minus square root b squared minus 4ac over 2. You know, remember the quadratic formula. Or you can expand it out and compare. You can factor out and compare the coefficients. Okay, so it's just an aside in algebra. And what we know is that this, so remember, L behaves like a polynomial in that the properties of this will be exactly the same as this. So applying this operation to y is exactly the same as applying this operation. The two things are equal to each other at this particular lambda 1 and lambda 2. Okay? So this is useful then, because now we can rewrite this AR2. We can simplify again the lag operator form. Namely then, well, we have this here. So this just means we have, putting this into the above, it means we have 1 minus lambda, like lambda on L. Okay, just plugging this into here, because the two things, this equals this, which takes us down to here. So all we've done is divide both sides by this 1 minus lambda L and 1 minus lambda 2L. And remember, we can do this division because L behaves like a polynomial. So we can divide both sides as if it was a polynomial. So we can now see, so we've just rewritten yt. So this here is the AR2 re-expressed. So we can see the benefit of this is that now what we've done here is literally write the AR2 into its infinite MA infinity form. This here is just going to be, is just a function of all now the lags of mu, of epsilon t. So for example, so we can see we need both of these roots to be less than 1 in absolute value. Okay, otherwise the system would blow up. So if this lambda 1, so take the case when, take the example where, to see why we need this condition for stationarity, why both of these roots have to be less than 1 in absolute value. Well, take the case, suppose not. Suppose for example, the second root was 1. Well, just divide both sides by 1 minus L. So in this case, we'd have if lambda 2 was 1, we'd have this. This would just be 1. Okay? So we'll divide through. Well, L behaves like a polynomial. So this is just a geometric progression. 1 minus 1 over L is just 1 plus L squared. Yeah, the geometric progression. And again, L behaves like a polynomial. So these two things are equal to each other. But remember, the lag of mu is just equal to mu, because mu is just a constant, so mu is the same every time period. So we can see that this is just, we're going to get infinity here. We're going to get mu plus mu plus mu plus mu an infinite number of times. So we can see that it cannot be stationary. Okay, so we can see why we have to have both of these roots less than 1 in absolute value. And again, for this course, we don't do formal proofs of this. You just need to know the result. So common questions on this will be to give you a process and for you to find the conditions when it will be stationary. So you just need to be able to state the result and find these roots and then give the conditions. But it does help to understand the intuition of why we need these roots to be less than 1. If they weren't less than 1, then the series would blow up, and that's why we need them both to be less than 1 in absolute value. So hopefully, write a question if you have one. Does everyone follow the intuition of this? The crucial part is how we can re-express this AR2 into this form here, generally. So for every different phi1 and phi2, we're going to get a different set of roots. Once we find them, we can re-express yt in this form. This here is actually just its MA infinity form. If we expand all this out, we can write it as a function of all the past lags of epsilon t. And we can see in order for it to be stationary, in order for it not to blow up, both these roots have to be less than 1. Okay? So once you understand it for an AR2, then it's exactly the same idea for an AR3 or a general ARP model. So we can do all the same thing again. We can have an ARP model, definition, simplify down, write it in its lag operator form. We now have a p-order polynomial in L, which means we can factor this p times. Again, this is just general result. Okay, you'd not be expected to, in the general case, this can only be solved for numerically anyway. For every different phi1s, we can get a different set of roots. Okay, and that's it. So then we can just divide, and we can do exactly the same thing as we did for p equal 2, but for the general p now. And again, if any one of these roots were 1 or more, the system would blow up. So we have to have that each of the roots for every j is less than 1. So this is just the general condition for the stationarity of an ARP. Okay, And again, please watch if you still have questions, please watch the video clip on this. It gives more detail on this as well. Okay, so that's it then. So that's, and then, so in armor PQ, well, we can do the exact same thing as before. It looks exactly the same now, we just got this extra MA bit here. We can still take this over here. We then have the lag operator form of a armor PQ. And again, we can do the exact same thing. The stationarity only depends upon the AR part, because this bit's always stationary. And MAQ is always stationary, because this here, each one's white noise, all these coefficients, the variance is finite and so on. So this part is always stationary. So the stationarity only depends upon the ARP part. So we can do the exact same thing. We need all these roots of this to be less than 1. So we can do something very similar to here. We're going to get all this again, but now we're going to get all these. You're going to get like e to 1 and so on here inside there. So it looks exactly the same. I don't know, but you're not. Are you? Which bit are you not following? It's not. I think it looks. Did you understand for the case of? Did you understand the AR2 example? Because, in all fairness, this is in terms of exam type question. Let's go back. Did you understand this for the AR2? Because that's the crucial bit. Well, was this okay? Felicia, did you understand this bit? Did you follow the AR2 example? It's not. I think it looks harder than it is. It's just something. The thing with the econometrics, it takes a while for it to sink in. So as we do exercise classes, and when you see past exam questions and so on, and as the course progresses, everything should slot together. But did you follow which bit are you struggling with? Did you follow how we can rewrite the AR2 into this form? While we can rewrite it into its lag operator form. Okay, so white goes to infinity. Well, we get down to here. Well, remember, as I said, so this. If you're still having questions, then after the. If you understand the. If you still have questions after this, then it's best to come to an office hour to ask more specific questions. But, so white goes to infinity, well, so if lambda 2 equals 1, we get this, okay? So we're going to get this part here. Expand it out. So again, treating L like a polynomial, we know if this is just geometric progression. So we're going to get 1 plus L squared, so on. So we get down to here. So we can expand it out. Well, this is just equal to 1 plus L back forever of mu plus 1 plus L forever of epsilon t. Okay. Well, this, remember, mu is a constant. So if we lag mu back, it's still mu. So remember, mu equals mu every time period. So the lag of mu is mu. The lag of squared mu is equal to mu, and so on. All of them equal, because it's constant. So this just means we're going to get mu plus mu plus mu an infinite number of times. So it'll blow up to infinity. So is that clearer? And we can also see that this is going to be all of the past shocks added together. So we're going to get epsilon t plus a lag of epsilon t plus the lag squared, and so on. Okay, so we can see that if the mean is non-zero, this goes off to infinity, and also this is the sum of all the past shocks where the effect of the past that die away. So this will have infinite variance, and this will have infinite mean. So we can see that we have to have lambda, both of these coefficients less than 1 in absolute value. So is that, could you,